This is another video in the series on the algebra-based first-year physics course. The website is sciencehelpnow.com. This topic is forces, otherwise known as dynamics. This section is 4.4, the differences and the relationship between mass and weight. I strongly urge you to download a copy of the New York State Regents Physics Reference Tables from the nysedregents.org website. Download a copy. I would keep an electronic copy on my device, and I would also print out, if you can, print out a paper copy and keep it next to you with your calculator. So here we have a chart of the physical quantities we're going to discuss in this video. Their symbols, their units, and whether they are scalars or vectors. All right, the first physical quantity we'll be discussing would be mass. For a more thorough discussion of mass, look at the previous video, all right, 4.3, okay? The symbol for mass is usually a lowercase m. The unit would be kilogram or gram. Now, in most physics calculations, for most constants that we use, we would want to use kilograms, not grams, all right? But either of those are basic units of mass. Mass is a scalar. That means when you, for example, here's a box, and I want to talk about the mass of the box, you can put a lowercase m in the middle of the box, or you can write m equals 2.0 kilograms, but because it's a scalar, we tend not to draw an arrow. We tend to reserve drawing arrows when the physical quantity is a vector. All right, so we tend, if you don't see an arrow, it's probably a scalar. All right, and if you do see an arrow, there's a good chance that you're talking about a vector. All right, now, the next physical quantity would be weight. Synonyms for weight: gravitational force or force due to gravity. That's why the symbol for weight is usually not a capital W, although occasionally you will see that. Usually the symbol for weight is force due to gravity, or gravitational force. The symbol would be capital F with a lowercase g. All right, again, representative of the fact that synonyms for weight would be gravitational force or force due to gravity. So you're getting the F and the G, all right, in there. The unit for all forces, including weight, of course, is the Newton. I'll be showing you later in this video how a Newton is really a kilogram meter per second squared. Right? I'll show you where that unit is derived from. Now, weight and all forces are vectors. So if you have a box and you want to show its weight, you're going to draw an arrow, likely from the center of the object, all right, and say Fg equals, weight is generally directed downward, so weight would be negative, for example, 20.0 newtons. Okay, and again, arrow, probably a vector. No arrow, probably a scalar. All right, and finally, acceleration due to gravity, the last physical quantity that we'll be talking about in this video. The symbol, acceleration due to gravity, or just plain acceleration, all right, because this is a type of acceleration. The unit, of course, would be meters per second squared. Since it's a vector, all right, you're going to show it with an arrow, but we tend not to put velocity or acceleration vectors on the object. We tend to put those arrows next to the object. So the acceleration of this object, which is falling near the surface of the Earth, is approximately 10.0 meters per second squared. We know that that's rounded up from Earth's more accurate acceleration, which would be negative 9.81 meters per second squared. But we like to round it up to 10 because it's so easy to multiply and divide by 10. All right, so A equals negative 10 meters per second squared, or G equals negative 10 meters per second squared. All right, again, we tend not to put acceleration or velocity vectors on the object. We tend to put them off to the side, above, below, etc. All right, so these are all the physical quantities we will be using in this video. Their symbols, their units, and whether they are scalars or vectors. Now, mass and weight are related, but mass and weight are not the same. How about a quick review of mass from the previous video all right, as we move into this video, which shows the distinction between mass and weight. All right, now, you have inertial mass. Very, very simple. The microwave has a small inertial mass. Inertia being the tendency of an object to resist acceleration or changes to its motion. The microwave has a small inertial mass. We'll put the microwave in outer space. The refrigerator has a large inertial mass. We'll put the refrigerator in outer space. So what this means basically is that if I give the microwave a push with a force of 120 newtons, for example, and I give the refrigerator the same push, 120 newton force, because the microwave has a small mass, all right, let's say 5 kilograms, and I can use this equation over here, F equals ma, or A equals F over m, and we'll be going into this equation in much, much more detail in a later video. A video about Newton's second law, all right? To calculate the acceleration of the microwave, we're going to take the force 120, F divided by the mass 5. The acceleration of the microwave is going to be 24 meters per second squared. So I give the microwave a push in outer space and whoo, away it goes with an acceleration of 24 meters per second squared, assuming this is a constant force. All right, so the microwave is going really, really fast. All right, now, the same push, all right, applied to the refrigerator. Let's calculate the acceleration of the refrigerator. All right, A equals F over m. F is 120. The mass of the refrigerator is 60 kilograms. 120 divided by 60. The acceleration of the refrigerator, 2 meters per second squared. Give it the same push, and it's not quite going as fast as the microwave. So this is inertial mass, the tendency of an object to resist acceleration. The refrigerator with a larger inertial mass has a much larger tendency to resist acceleration. So his acceleration is small. The microwave with a small inertial mass has a much smaller tendency to resist acceleration. So his acceleration is very large. Now, I just want to mention that we are going to take all the stuff that we put in outer space and bring it back down to Earth, because we have a really big problem with garbage being left in outer space. That would be dead satellites, satellites that have crashed, bits of rockets, tools that astronauts have lost, etc., etc., etc. There is so much space garbage orbiting the Earth right now that scientists are very, very worried about an object as small as a marble or even smaller crashing through a space station or crashing into a satellite and destroying it. You could have a $1 billion or a $50 million satellite destroyed by a little piece of garbage as small as a marble crashing into the satellite, or you could have a space station and have a piece of garbage crash into the space station and possibly injure or maybe even kill an astronaut. All right, so we're going to take all of our stuff that we've been using and bring it back down from outer space. We're not going to leave the microwave and the refrigerator in space. We're going to clean up after ourselves. Here we are again in outer space, and this time we'd like to look at the difference between a large gravitational mass and a small gravitational mass. We have here an apple floating in outer space. We're floating in outer space. And here's the Earth, also in outer space. And what we have is a coin. All right, now this is the kind of coin that is given out at the parade at Mardi Gras in New Orleans. I happen to have this coin here from the parade at Mardi Gras. All right, so if this coin is floating past the apple and the Earth, and it is the same distance from the apple and from the Earth, all right, is the coin going to be attracted toward the apple with a smaller gravitational mass, or is the coin going to be attracted toward the Earth with a larger gravitational mass? Which object is going to win in the gravitational struggle to acquire this coin? Well, I'm sure you would agree that if the coin was floating by, equidistant, the same distance from the apple and the Earth, that the Earth would win. the Earth with a larger gravitational mass puts a stronger gravitational force on the coin, and the coin would be attracted toward the Earth. The apple is not going to win. All right, so this is gravitational mass. Now, again, the inertial mass and the gravitational mass are the same mass. And from now on in the course, we're just going to say mass. But there's a different way of measuring and looking at mass, whether you look at it from an inertial perspective or a gravitational perspective. I'll give you one more example of gravitational mass in just a moment. Oh, and again, make sure you clean up. All right, do not leave your apple in outer space. You can leave the Earth there. Do not leave your garbage in outer space. Big, big problems for satellites and for space stations and for our future. No garbage in outer space. Very quickly, a look at gravitational mass in a slightly different way, illustrating the same concept. All right, so we have the Earth, all right? We have a microwave floating in outer space. We have a refrigerator floating in outer space near the surface of the Earth. So the center of the microwave would be the same distance as the center of the refrigerator from the center of the Earth. Keep everything else the same. Because what we'd like to look at is the difference in the gravitational mass of the microwave, which we said earlier was 5.00 kilograms, versus the gravitational mass of the refrigerator, which is 60.0 kilograms. And what you find using this equation, all right, Fg equals m times g, and we will be getting into that equation during this video, all right, is that g for the Earth, the acceleration due to gravity, g or a type of acceleration, is negative 10 meters per second squared. All right, so if you take the gravitational mass 5 and multiply it by 10, all right, you find that the gravitational force that the Earth is able to exert on the microwave is negative 50 newtons. Now, why is the Earth able to exert a much larger gravitational force on the refrigerator? Because the refrigerator has a much larger gravitational mass. The gravitational mass of the refrigerator, the mass of the refrigerator is 60 kilograms. So Fg equals m times g, 60 times the same Earth, the same 10. 60 times 10 gives us 600 newtons. So again, because the microwave has a smaller gravitational mass, the Earth exerts a small gravitational force on the microwave, the weight of the microwave, right, at this height, all right? And because the refrigerator has a much larger gravitational mass, the Earth is able to exert a much larger gravitational force on the refrigerator. Now remember, inertial mass, gravitational mass, for the rest of this course, we're just going to say mass. We're not going to worry about how we determined, how we calculated that mass. Did we give it a push and try to see how fast the object accelerates, or did we see how strongly the object attracts other objects, or how strongly the object is attracted by other objects? It doesn't matter. It's all the same mass. And again, let's take our space junk and let's not leave it in outer space. I'm going to take my microwave and my refrigerator back down to Earth. I'm going to keep the microwave. Does anybody need a gently used refrigerator? I'll drop it off. Now we're going to make this absolutely clear. First of all, inertial mass, gravitational mass are just mass. It's the same mass calculated in different ways. So we're just going to call it mass from now on. And furthermore, the mass of an object does not change when you move the object to different places on Earth or different places in the universe. It doesn't matter. The mass of an object does not change. For example, I have a nice red bowling ball in my house. All right, here's my nice red bowling ball. There's the little holes so I can put my hand in it and go bowling. All right, if I take my bowling ball and put my bowling ball on the moon, all right, my same bowling ball on the moon, not to scale, if the mass of my bowling ball, m, is 6 kilograms, on the moon, the mass of my bowling ball is still 6 kilograms. All right, so whether I have my bowling ball, all right, on the moon, all right, in my house, or floating in orbit around the Earth, all right, there's my bowling ball, all right, the mass of my bowling ball is still 6 kilograms. I can put my bowling ball on Jupiter. Not really on Jupiter. Jupiter's a gas giant, but let's just make believe. If I put my bowling ball on Jupiter, the mass of my bowling ball is still 6.00 kilograms. If I drop my little red bowling ball on the little red planet called Mars, right, the mass of my bowling ball is still 6.00 kilograms. The mass does not change when you move an object or a sample of matter from one place in the universe to another. To be absolutely clear, on Earth, let me just move the Earth here. To be absolutely clear, on Earth, all right, I can put my bowling ball at the top of a mountain, the bottom of a valley, all right, or at sea level, all right. I can put my bowling ball on Earth at the top of a mountain. It's still 6.00 kilograms. I can put my bowling ball at the bottom of a valley, way down there, maybe at the bottom of the ocean. All right, here's the ocean. Get rid of the moon. Here's the ocean. I can put my bowling ball at the bottom of the ocean. All right. I can put my bowling ball at sea level. All right, anywhere on the Earth, the top of Mount Everest. Okay. Very dangerous place. I'm going to get somebody else who's going to Mount Everest anyway to put my bowling ball up there. All right, so top of Mount Everest. All right, wherever you put the bowling ball, it doesn't matter. The mass of the bowling ball at the bottom of the ocean is 6.00 kilograms. The mass of the bowling ball at sea level is 6.00 kilograms. The mass of the bowling ball at the top of a mountain is 6.00 kilograms. Down in the valley, Death Valley, right? The mass of the bowling ball is 6.00 kilograms. Any place on Earth, any place in the universe, I put my bowling ball, the mass stays at 6.00 kilograms. So now that we've thoroughly discussed what mass is, well, what is an object's weight? We're going to deal with a common usage in physics in which we'll focus on, for example, small objects resting on the surface of or orbiting a much larger object, like a moon, a planet, some celestial body. So the weight of an object is a measure of the gravitational force exerted on it as a result of its interaction with a second object. And we've looked at this before in other videos, in earlier videos. So you've got two masses here, the man and the Earth. The man is standing on the surface of the Earth. All right, and so the Earth attracts the man downwards, and the man attracts the Earth upwards. All right, so when we're talking about the weight of the man, we're specifically focusing on the gravitational force that the Earth exerts downward on the man. Okay, so this is the man's weight. All right, Fg, the man's weight, let's say he's negative 700 newtons. All right, whatever he is. Okay, so in our common usage, common language, and commonly in physics, all right, we're talking about the gravitational force, one of a pair of gravitational forces, but we're focused on the gravitational force that a much larger body exerts downward on a smaller body. Right? That is the man's weight. The weight of an object can be different in different locations. or on different celestial bodies, different locations. Now remember, when we were talking about the bowling ball earlier, we said no matter where you put the bowling ball, the mass of the bowling ball is 6 kilograms. The mass of the bowling ball on the surface of the Earth is 6 kilograms. The mass of the bowling ball, all right, on the surface of the moon is still 6 kilograms. Now, what about the weight of the bowling ball on the two different planets? Now, the Earth exerts a much greater gravitational force downward than the moon is able to do. All right, so we'll make this vector much smaller. All right, so this represents the gravitational force that the Earth exerts on the bowling ball. The moon does not exert as great a gravitational force on the bowling ball. So this vector is larger. This vector, arrow, is smaller. Remember, weight is a vector. Mass is a scalar, no arrow. Weight is a vector. So the weight of the bowling ball on the surface of the Earth is approximately 60 newtons. We can say negative 60 newtons. Weight definitely pulls downward on an object. And on the moon, the weight of the object, let's round it off. Let's round it up a lot and say that the weight of the same object on the moon would be approximately 10 newtons. Approximately 1/6 the weight that it would be on Earth. Now, the ability of an object to attract another object gravitationally is based upon its mass and also on its radius. In this video, we'll discuss mostly from the point of view of the different masses of the objects that are doing the attracting. In the next video, we'll see how radius falls into that scheme. All right, so again, the mass of the bowling ball always stays the same. The weight of the bowling ball might be different in different places on Earth or different celestial bodies. Let's see why. If you have the worksheet that accompanies this video, or if you are taking notes, copy down these vocabulary words, study these definitions. If you are just watching the video, read through the definitions, make sure they make sense to you, and pause the video as necessary. Don't just copy the definitions that you see here. What you should do is first try to come up with your own version of the definition of these various words and phrases, and then see how close your definition is to the definitions that are given here or in another physics textbook or on the internet, right? A source of your choice, right? See how close you come to writing a good definition for these words or phrases. In other words, challenge yourself, practice, see if you know what you're talking about. All right, so here we have a definition for weight, which we've gone over extensively in this video, and also a summary of the difference between mass and weight. The mass of an object does not change with location. If I'm standing on the Earth and my mass is 70 kilograms, if I travel to the moon, my mass is still 70 kilograms. Weight, on the other hand, can change if you change your location. Now, for example, if I'm standing on the Earth and my weight is 700 newtons, and I take 2 steps to the right, my weight would still be 700 newtons. But technically, if I go to the top of Mount Everest, my weight will be slightly less. And if I travel to the moon, my weight will be a lot less. So the weight of an object can change when the location of the object changes. So we look at the question, do you weigh less on the top of Mount Everest than you do, let's say, at sea level or down in a valley? And the answer is, well, that depends. How many significant figures are we talking about here? Now, these numbers are completely made up, other than the fact that 752 newtons is a reasonable number of newtons, a reasonable weight for a kind of an average person that weighs about 165 pounds. But other than that, the numbers are completely made up. What we're trying to illustrate here is the role of significant figures in trying to answer the question accurately. Well, do you weigh less on the top of Mount Everest? Now, the first thing you want to know is that the farther you are from the center of the Earth, yes, technically, the less you weigh. As you get closer to the center of the Earth is able to pull you more strongly, and you would weigh more. Now, this discussion is getting into the radius of the planet, which again, we will go into with a lot more detail in the next video. But for now, it is absolutely true that the farther you are from the center of a planet or a moon or a star, whatever it is that you're near, the less you are going to weigh. Now, for example, a rough example. A woman is flying in an airplane, so she's way above the surface of the Earth. She's very far from the center of the Earth. Let's say that her weight flying in the airplane up here, right, here's the valley, here's the mountain, here's sea level, okay, bottom of the ocean, okay? So flying up here in the sky in an airplane, her weight is 752.3740 newtons. So we've got 1, 2, 3, 4, 5, 6, 7 significant figures. Now, at the top of Mount Everest, which is below where planes usually fly, most commercial planes are flying up around maybe 7 miles up in the sky. The top of Mount Everest is about 5.5 miles up. All right, so at the top of Mount Everest, all right, you're going to weigh a little bit more. That same woman is going to weigh a little bit more. So instead of 752.3740, here she weighs, for example, 752.3743. All right, she weighs a little bit more. Okay, now going down to sea level. All right, at sea level, which is a little closer to the center of the Earth, maybe she weighs 752.3746 newtons. Oh, missing my newtons here. Put my newtons in. All right, so at sea level, if she's standing here, maybe she weighs 752.3746. She weighs a little bit more than she does at the top of Mount Everest. Now, if she steps to the right and stays at the same distance from the center of the Earth, of course, her weight is the same, 752.3746. All right? So it's not so much that changing your location changes your weight, but changing your distance from the center of the planet or the moon that you're measuring your weight on changes your weight. Stepping to the side, your weight doesn't change. All right, now, down at the bottom of a valley, all right, down here, let's say we're down here at the bottom of Death Valley. And since you're closer to the center of the Earth, she weighs a little bit more, 752.3747. Again, these numbers are completely made up. The point that I'm looking to make here is that if you were to round all of these weights to, let's say, for example, 3 significant figures, which is a common number of significant figures for us to use for most high school and possibly college applications, all right, what would her weight be if we were just reporting it to 3 significant figures? Well, to 3 significant figures, her weight would be 752 newtons. This number here is not 5 or greater, so we don't change this. We're not rounding up to 753. All right, her weight here would be 752 newtons. That's to 3 significant figures. Well, what's her weight here to 3 significant figures? Well, it's still 752 newtons. What's her weight here to 3 significant figures? Well, it's still 752 newtons. What's her weight at the bottom of a deep, deep valley? Well, it's still, boom, 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 752 newtons. So yes, technically, as you get closer to the center of the Earth, yes, your weight increases. But if it increases at a very small decimal, you're not going to notice that decrease if you only round to 2 or 3 significant figures at the very high end of that weight. All right, we're rounding over here. All right, when the differences are way down here at the, let's see, tenths, hundredths, thousandths, at the 10,000ths place. And again, these numbers are mostly made up. All right, what we're trying to illustrate is the role of significant figures in discussing the question, well, do you weigh less on the top of Mount Everest? So the answer would be, well, yes, you do weigh less on the top of Mount Everest than you do at sea level, but you might not notice the difference if, depending on how many significant figures you're rounding those two answers to. So, how do we calculate the weight of an object on different celestial bodies, or even floating in space near different celestial bodies? Let's start by calculating the weight of an object on planet Earth. Now, here's the equation, the general simple equation for calculating weight, which is also known as gravitational force. So weight equals mass times acceleration due to gravity. Fg is the weight, or the gravitational force. There's the unit for weight. M is mass. The unit for mass would be kilogram. And g is the acceleration due to gravity of the celestial body that you're talking about, the Earth, the Moon, Jupiter, whatever. Now, the unit would be meters per second squared, and for the Earth, the acceleration due to gravity of the Earth is negative 9.81 meters per second squared. We're going to use negative 10 meters per second squared. Now, there is a more complicated equation for calculating weight. I'll show it to you quickly. Fg equals big G m1 m2 over r squared. We will look at this equation in the next video, 4.5. All right, so for now, we're going to use the simplified version right here. Okay, and here we go. Let's do this problem. Let's calculate the weight of a 50-kilogram student. Now, remember, when no other celestial body is mentioned, you assume it's on Earth. So, what are we given here? Calculate the weight. All right, so we're trying to find the weight of this student. All right, this is the question that we're being given. Calculate the weight. Now, 50 kilograms is the mass. M equals 50.0 kilograms. We're assuming planet Earth, so we know that the acceleration due to gravity is going to be negative 10 meters per second squared. Now, some people will emphasize that this is negative and emphasize that the answer is negative. Some people will just forget about the negative. All right, keep in mind it's a weight. All right, so we know that it's negative. All right, but whether your teacher says, okay, the answer is positive, negative, if your teacher doesn't care, I don't care. All right, but keep in mind weights are down. A weight force is directed down, so technically it's negative. All right, and technically G is also negative. All right, so remember also that G is a type of acceleration. That's why the unit is meters per second squared. with what we have given here, we know that the equation we're going to use is going to be Fg equals m times g. All right. So plug in the mass. All right, 50.0 kilograms. G, all right, negative 10 meters per second squared. If your teacher wants you to use 9.81, then by all means, put in 9.81 here. Whatever your teacher or professor says, okay, is the way you want to do it. All right, so Fg is equal to 50 times 10, all right? So that's negative 500. Now, let's look. First of all, we've got 1, 2, 3 significant figures, 1, 2, 3 significant figures. So by putting the decimal point there, we're emphasizing that these three are all significant figures. Now, the unit, kilogram times meter divided by second squared. The technical unit is the kilogram meter per second squared, but we know, of course, that that is a Newton. So the weight of the student is negative 500 newtons. All right, or you could write kilogram meters per second squared. How do you convert masses to weights on Earth as simply as possible? Well, you just multiply the mass by 10, right? Fg equals the mass times g, which for the Earth is 10. Take the mass, multiply by 10, you're done. On Earth. If it's the moon or Jupiter, it's going to be different, right? But, so what would the weight of a 2 kilogram, let's say miniature watermelon, what would that be? 2 times 10. The weight of that little watermelon would be 20 newtons. Okay, what about a half kilogram hero sandwich? Multiplied by 10. Well, you're just moving the decimal over 1, right? So that would be 5 newtons. That hero sandwich would weigh 5 newtons. All right, what would the weight of a 10 kilogram child be? All right, multiply by 10. That would be 100 newtons. You see how simple it is? Take the mass, multiply by g, which for Earth is 10. Just take the mass, multiply by 10, take the kilograms, multiply by 10, you get the newtons. A 4.5 kilogram Chihuahua dog, what would his weight be? That's his mass. What would his weight be? Boom. All right, 45 newtons. And finally, what would the weight of a 75 kilogram man be? This is his mass. His weight would be, that's right, 750 newtons. And remember, a newton is really a kilogram meter per second squared. So you could also say 5 kilogram meters per second squared. You could change all those newtons to kilogram meters per second squared. Have at it. All right, very, very simple. Take the mass, multiply by 10, you got the weight. Bam. Now let's calculate the weight of the same student on the moon. Now remember, his mass is still 50 kilograms, but his weight on the moon is going to be different. All right, what are we given? Calculate the weight. We're being asked, all right, we're being given this problem. What's the weight in newtons? Okay, a 50 kilogram student, so the kid's mass, all right, is 50.0 kilograms. Since we know it's the moon, we can look up the acceleration due to gravity, all right, g for the moon. We can look that up on the internet. We can look it up on a chart, all right. So look it up on the internet, look it up on the chart. Sometimes they're going to say it's 1.62 meters per second squared. You might find 1.63, 1.64. I don't think your teacher or professor is going to worry too much whether it's 1.62, 1.63, or 1.64. All right, if your teacher gives you a specific acceleration due to gravity for the moon, use it. All right, if not, anything in that range would be fine. All right, so now keep in mind also in physics and chemistry, in order to get credit, you must do 3 steps to every problem. First, you write the equation, FGmg. All right, this is what I have in this problem. So I think the equation that I'm going to be using is this one. Fg equals m times g. Step 1, pick an equation. Step 2, plug in with the correct units. So here we go, 50. All right, m is 50 kilograms. And g for the moon, all right, g for the moon, and this is going to be his weight on the moon, okay, is negative 1.62 meters per second squared. Okay, so now we need to do the math. Take your handy dandy calculator. 50 times 1.62. Okay, 81. All right. So his weight on the moon, all right, is negative 81.0, all right, newtons. Okay. Now remember again, a newton is the same as a kilogram, right? If you're multiplying kilograms times meters per second squared, right? The kilograms are over 1. So you're going to get kilograms and meters on top, seconds squared on the bottom. All right, so 81.0 kilogram meter per second squared would be the same thing as negative 81 newtons. Okay, now you should also come back here and put the answer in here. All right, there's the answer that you calculated. All right, it's not a question anymore. We got it. You don't have to erase it. Okay, so we keep in mind that on Earth, his weight, we just did the problem, his weight was 500 newtons. On the moon, his weight is only 81 newtons because the acceleration due to gravity on the moon is 1/6, much less than the acceleration due to gravity of the Earth. This time, we're being asked to convert a weight to a mass. Now, to do that, of course, again, you have to know what planet or celestial body you're talking about. Here we go. Space Dog weighs 40 newtons on Earth, 6.48 newtons on the moon, and 103.8 newtons on Jupiter. All right, keep in mind, Jupiter pulls down stronger, so you're going to weigh more on Jupiter. The moon is not as strong. The moon does not pull down as strongly, so you weigh less on the moon. All right, show the work to calculate her mass, Space Dog's mass, on each celestial body. Now, we were given 3 different weights, 1, 2, 3. We know that we're going to look up g, the acceleration due to gravity, for the Earth, for the moon, and for Jupiter. All right, so basically we're going to have Fg, which we were given, g for each celestial body we're going to look up, and we're trying to find the mass of this little dog on each planet. And we're supposed to show the work 3 times. All right, now we know the equation that we're going to be using is Fg equals m times g. But we're being asked to calculate m. So we need to get m by itself on the left side. To get m by itself, I'm going to divide both sides by g. These g's are going to cancel, and the equation that we're going to use, the version of this equation that we're going to use is m equals Fg over g. We're going to use m equals Fg over g. So what I'm going to do now is erase the problem so that we have lots of room to show the calculations for Earth, for the moon, and for Jupiter. So we're trying to calculate the mass of the dog, first on Earth, then on the moon, and then on Jupiter. All right, so here we go. Mass is equal to Fg divided by g. All right, step 1, we wrote the equation. Step 2, we're going to plug in, all right, using the correct units. All right, Fg, all right, we've got 40 newtons divided by negative 10 meters per second squared. 40 divided by 10. The mass that we get, 40 divided by negative 10, the mass is negative 4 kilograms. And you say, wait a minute, mass can't be negative. What's going on? And you realize that if you're going to make your G negative, then you have to make your weight negative also. All right? And then the mass comes out positive, as mass must come out. If your mass comes out negative, there's some minor mistake somewhere with signs, all right, or maybe it could turn into a major mistake. All right, so again, if you're going to use a negative G, then you need to make the weight negative also, because mass has to come out positive. Most of the time also must come out positive. All right, let's try the next part here. What is the mass of this puppy space dog on the moon? All right, I'm going to remind you that step 1 is to write the equation in the format that you are going to use. All right, that's why we're not writing Fg equals m times g. We're trying to find the mass. So the mass is by itself on the left side. All right, so here's the equation. M equals Fg over g. All right, plug in. All right, remember, we're going to make our weights negative here. So we're going to plug in Fg. All right, M equals negative 6.48 newtons divided by the acceleration due to gravity on the moon, negative 1.62 meters per second squared. Okay, divide those, 6.48 divided by 1.62, divided by 1.62, and voila, we get that the mass of Space Dog is 4 kilograms. All right, well, of course we're getting the same mass. When you move an object from one celestial body to another, the weight will likely change. The mass does not change. So we got 4 kilograms, we got 4 kilograms, and here we go on Jupiter. All right, so M equals Fg divided by g. There's step 1, write the equation. Step 2, plug in. All right, M equals, make that a little smaller there, negative 103.8 newtons divided by the acceleration due to gravity on Jupiter, 25.95 meters per second squared. All right, and class, you'll see the mass of the acceleration due to gravity of Jupiter listed as 25 point something, 24 point something. As long as it's close, you're okay. All right, so the mass, Space Dog's mass on Jupiter is 103.8. 8 divided by 25.95. Oh my goodness, it's 4 kilograms again. Okay, so, all right, on different celestial bodies, Space Dog's weight changes, but her mass does not change. She has the same mass on all the different celestial bodies. Now, the reason that the mass does not change can be explained that mass is an intrinsic property of the sample of matter. All right, mass is an intrinsic property. Mass depends only upon the object that you are measuring, but weight is an extrinsic property, which also depends on how something else affects that object. And what it is that affects the weight, Fg, what affects the weight, to change the weight, Fg, is the acceleration due to gravity of the planet or a celestial body that the object is resting upon or orbiting or falling toward. It just has to be near the celestial body. Just a quick note about the weights of objects whose masses are given in grams. So if you're given a mass in grams, the first thing you're going to do is convert the grams to kilograms, knowing that 1,000 grams is equal to 1 kilogram. Probably you want to use factor label method. All right, and then convert the mass in kilograms to weight in newtons using this equation. Fg equals m times g. Keep in mind, all you're really doing is taking the mass in kilograms and multiplying by 10 to get the weight. All right, so don't try to convert masses in grams straight to newtons. Rather, convert them first to kilograms and then convert the kilograms to newtons. What's the simple and easy way to convert a weight in newtons back to a mass in kilograms? On Earth, of course. Well, since the mass is equal to the weight divided by the acceleration due to gravity of the planet you're on, for Earth, the acceleration due to gravity is 10 meters per second squared. All right, so all you're going to do is take the weight and divide by 10. All right, so calculate the mass of a 30 Newton house cat. All right, so very simply, we take the weight, all right, 30, and divide by 10, all right, which is really, according to this equation, taking 30 newtons, dividing by 10 meters per second squared, all right, and we get that the mass of the cat is 3 kilograms. All right, so if you're just going to do this in your head, take the weight of the cat, divide it by 10, and you've got the mass of the cat, 3 kilograms. So the answer to this question, all right, the answer to this question, to convert an object's weight, now that would be on Earth, of course, to its mass, comma, take the mass. The mass has to be in kilograms, of course, and divide by 10. Okay? Very, very simple. So let's convert these weights to masses in our head. Do these problems quickly in your head, convert the weights to masses. All right, so we're just going to take the weight in newtons and divide by 10. So this is 1,500, 1,500. We've got a significant figure here, here, and here. That's what that little line means. So I'm just going to divide by 10. All right, and the answer is going to be 150 kilograms. And I do not like the way that marker is writing. Let's try a different marker here. All right, so 150 kilograms. All right, divide by 10. Okay, 700 newtons becomes 70 kilograms. Okay, make that a little darker. Not much, all right. 1.5 newtons, right, becomes 0.15 kilograms. All right, 12 newtons becomes, oh, and you know what, here, we've got 1, 2, 3 significant figures here. That's what this little line means. The 0 is significant, so we've got 3 significant figures. We should put that there. Here, let's see, was that there to begin with? Yes, it was. That dot was there, I think. I think that dot was there. If that dot was there to begin with, then we've got 3 significant figures here. So it's technically 70.0 kilograms. All right, there, 2 significant figures. All right, here. All right, we've got 1.2 kilograms. All right, and here, 0.01. All right, move the decimal place that way, right? The same way we've been doing here. And we're getting 0.001 kilogram, which is 1,000th of a kilogram, which is 1 gram, right? 1,000th of a kilogram would be 1 gram. I'm sorry, I skipped all the, what are these things? We've got a 1,500 Newton motorcycle. We've got a 700 Newton woman. We've got a 1.5 Newton tomato, a 12 Newton kitten, and a 0.01 Newton paperclip. All right, and 0.001 kilograms here becomes, really that's 1 gram. That's tenths, hundredths, thousandths, 1,000th of a kilogram would be a gram. All right, so we have very quickly converted all of these weights to masses by taking the taking the weight in newtons, dividing by 10 to change it to kilograms on Earth.